All right. Good evening, class. All right. Today, what we're going to be looking at, and we've already talked about it a little bit, and that's centripetal acceleration. Centripetal acceleration. We're going to be looking at centripetal acceleration. We're going to be looking at centripetal force. One of the trick questions I use on tests a lot of times is this. Talk about something moving in a circle. And I'll give people a question on test, and I'll say, all right, something is moving in a circle. So let's draw a little circle. So there's something's kind of moving in a circle. And I'll say, is it accelerating? I'll say, first of all, it's moving with a constant speed. So it's not speeding up, it's not slowing down, it's moving with a constant speed. So is it accelerating? At which point most people then say, no, it's not accelerating, it's not changing speed. You got to remember something. The equation for acceleration, here, this is like 10th grade. Acceleration is equal to change in velocity over change in time. Remember, velocity is not just speed. Velocity is speed with direction. So, at this point, you can see that the velocity is straight up. Look at what happens by the time you get up to here. Look at this part. At this point, the velocity is pointing this way. So, you can see the velocity is changing because direction is changing. Matter of fact, even if we took a look at from this point to this point, the velocities are changing. This velocity is always at 90 degrees to the radius. That's why this is called some people say VT. They'll call this a tangential velocity because it's at 90 degrees to this plane on here. So here's our tangential velocity. And now what's actually kind of neat, and I'm not going to attempt to draw this to scale, but if you could subtract the first velocity from the second velocity. So if you could subtract those two velocities from each other, you would actually see the change in velocity points towards the inside of the circle. So that means there is an acceleration, and that acceleration points to the inside of the circle. And that's what centripetal acceleration is. So here we can sit here and take a look. The equation for centripetal acceleration is AC equals V, technically VT square over R, but I will admit I'm too lazy to write the T out when I do those questions. But anyway, so VT square over R. So now what I can come back and also say is I can give one more equation to combine into this. And the other equation is this. Think about it. If you've got a rope and you're swinging something around in a circle, if you let go of the rope, it doesn't move in a circle anymore. That's because if there's an acceleration, thank you, Mr. Isaac Newton, we know that there has to be a force. Force is equal to ma, and so now we can come back and say, well, wait a second. This force is a centripetal force, so it's going to be equal to your mass times your centripetal acceleration. Now, here's what's funny. We don't use this equation a whole lot. What we usually do is just substitute. And we go ahead and rewrite this as force equals mv squared over r. One of our most common things in like physics team and everything like that is things that are equal to mv squared over r. Let's just say you've got a rope swinging something in a circle. Well, for that problem, tension in the rope would be equal to mv squared over r. What if you've got, I don't know. Let's say, for example, maybe you've got a car going around the curve. Well, if you've got a car going around the curve, what is equal to mv squared over r? Well, what is it that holds a car on the road? Dun, dun, dun. You ever notice on wet days how it's so much easier to go off the road? That's because it's friction. What's the equation for friction? Mu n. Now, if you look at this, what's neat is your n on the flat ground is mg, so your m's cancel out. So that's a pretty common thing. All right, this is your two basic questions here. Look like this. Now, we can have a little bit more fun and throw some extra stuff into these problems. We can also take a look at what's known as a vertical circle. I'll say this, vertical. So, I'm going to draw me a little picture of something moving in a vertical circle. We can think about like a Ferris wheel. Although I don't know that I've seen a Ferris wheel in a long time, but I don't spend a lot of time at the fair, so who knows. So, if we take a look at this, a vertical circle like this, let's say that there's a rope or a string, something attached, pulling towards the inside. And I'm going to put a little T here and a T here. The question is, in both these situations, all I want to know is what is equal to mv squared over r. I want to know for the top, and I want to know for the bottom of this circle. So I got two situations that I want to identify in mv squared over r. In both cases, we've got a tension. What changes is this. At the top, the weight is actually helping to make this centripetal force. So at the top, we're going to write T plus mg. Both of those combine to make the mv squared over r. At the bottom of the circle, the weight is actually going in the opposite direction. So we've actually got a T minus mg. So if you were asked where the greatest force is on something traveling in a vertical circle, the greatest force is going to be at the bottom of the circle. That's where your tension is going to be the greatest inside here. Now, I'm going to throw one more equation at you, and then we're going to do a couple of examples. One other special situation is what we might refer to as being weightless. What is it to be weightless? Chances are all of you have felt it before, because let's face it, we do stupid stuff sometimes. We jump over hills in cars. Have you ever went over a hill in a car, and you went over a little bit too fast, and you felt your stomach go, huh? That one little second right up there. There used to be where I went to college, there's a hill called Broadwell's Mill Road. And I used to fly through there in my truck. And I wasn't the only one, because there's a hill you could literally jump, and you could actually have that weightlessness, and your rear end would usually whack. The asphalt was all chewed up on that side from everybody jumping the hill and bottoming out their rear ends. But you'd get that little feeling in your stomach. What weightlessness is you're not actually, if you're anywhere on earth, you actually have weight. If you're in an airplane that's plummeting to the ground, you still technically have an mg. What makes us feel weight is because of what we're sitting on. So when you jump a hill or go over something too fast, if you go over it fast enough, what will happen is the only thing providing force is your weight. No tension, just the weight. So what happens is you've got this situation. Now if you look, your masses cancel. So this is what we kind of call our equation for weightlessness. If you can go fast enough and jump the right hill, you can actually feel weightless at the top of that hill. And that's where you get that little funny feeling in your stomach at that point. Ouch. All right, so let's do a couple of problems. Let's take a look at the homework. Now, I've only got two problems I want to do. So let's take a look at example D. And I don't know if you can read this, but that's why you've got homework. It's okay. So we've got a car, about a test car moving at a constant speed around a road of radius 50 meters. So here's the problem. So we've got a car. I'm going to draw me a little radius here. So there's my radius. We've got a car, and I'm going to draw its tangential velocity. So it's got a speed, a straight line velocity of 10 meters per second at this point. All right. And it says it has a radius of 50 meters. So there's the two pieces of information that tells you about this car. Part A says find centripetal acceleration. Well, it just so happens I've got an equation just for that. V squared over R. So all I have to do is come in here and go 10 squared divided by 50. Oh my goodness, leave your calculators at the house. Look at that thing. 10 squared is 100. 100 divided by 50 equals 2. Now this is still an acceleration. So the unit is meter per second squared. No different than any other type of acceleration. But do notice how I did put the little C on here to say that this is a center-seeking centripetal acceleration in this question. All right. Part B says find angular speed. So B asks for you to find angular speed. Well, angular speed is W. Well, if you remember, we've got an equation that says V equals RW. This problem told you V. It said V is 10. There's R, so what's W? So V is 10. Now we can come back over here. R was 50. So what is W at this point? Come on, you can do it. 2/10, very good. Keep going, which would be 0.2. Now this is that crazy thing about W we've talked about before. The unit is radians per second, and the radians literally just appear out of thin air. Because what you've got is this. I'm going to do the units for this. I'm going to slide over here. Velocity is in meters per second equals, this would be a meter times W. When you divide, your meters cancel. So there's like nothing over second is W. And then just like magic, bam, radians appears. And that's a crazy thing about radians. It's why we got to work all these problems in radians in the first place. All right, so your two answers to the first question. Answer to question A is 2 meters per second square. The answer to the other one is 0.2 radians per second, or rads per second. All right, so that one was kind of easy. Let's take a look at one other example. Next example. A car travels a speed of 30 miles per hour. On a level turn, what is the minimum friction needed to hold it on the road? So a car is traveling into a turn. Here I'm going to draw my same little drawing again. I'm going to draw that up. The car, it says, has a velocity of 13.4 meters per second. It even gives us a radius. It says a radius of 50 meters again in this problem. All right, so it's give us a velocity, it's give us a radius. Next thing it says is what is the minimum minimum friction needed to keep the car on the road? Here's the thing. This is one of those questions that's like, what is equal to mv squared over r? For a car to go around the curve, it's friction. So we'll say mu n, this car is on flat ground. We could do a little free body over here. We'd have our normal force going up, our weight going down, mg. So our normal force would be equal to mg. So this is mu mg equals mv squared over r. Now take a look what happens to your masses. That's why it didn't give us the mass. It asked us to find mu, so let's get rid of that g. So mu would be equal to v squared over g times r. And that's all we've got to do to get our answer. It said that v is 13.4. G, of course, is 9.8 times r of 50. This is going to be like 13.4 over 490, but here we go. We'll break out the trusty Casio. 13.4 square divided by 490, which is the product of 9.8 and 50. And the answer is 0.37. And if you remember, coefficient of friction does not have a unit, so it's just 0.37. What would happen if you worked a problem like this? A car going around the curve and your answer came out, let's say your answer came out like 1.2. What would that tell you about the car going around the curve? Well, if you remember, there can't be a mu greater than 1, so guess what's going to happen to the car? It's going in the ditch. You're going to wreck. So, if you work one of these problems and your mu comes out greater than this, that's your problem. Now, one of the problems you work, and it's probably the hardest problem you'll work, and I will probably be the one to have to do that. It's going to be basically a NASCAR question. Yeah, NASCAR, those cars travel too great a speed for friction to hold them on the road. So what does NASCAR do so that the cars can stay on the road? I'm looking around. They bank the turns. The whole reason for banking the turns is to keep the cars on the road. So in this case, you can bank, and that banking will actually provide an mv squared over r. This is a pretty tricky little problem to work where because you've got your mg going down, you've got a normal force that's actually up like this. So you've got to find a component. And I'm going to work that one, so I'm not going to go into it too much. All right. Problems I want you to go ahead and try. Most of them are kind of easy. 17, the only trick in 17, it says something about revs per minute, so you've got to change that to rads per second. It even gives you 10 inches. You need to convert that, but it's mainly just a V equals RW question and a centripetal acceleration question. Let's see. Let's do 17, 18, 19, 21. It's a car in a curve, so that's our mu n equals question right there. And then let's do 23. I'm not going to ask you for a lot, but today let's go ahead and get in these 5 after we finish the lesson. So there's a question about merry-go-round, which means this is going to be a question that's got the top and the bottom. And just remember, at the top, you've got a t plus mg equals mv squared over r, while the bottom is t, come on, minus, very good, equals mv squared over r. All right. And as always, I love you. He says physics teachers can't have a heart, right? Hey, man, where's my mouse? There it is. Oh, you stupid.